So now let's look at some other indeterminate forms. So ones that where we can't immediately apply L'Hopital's rule. So forms like 0 times infinity, 0 to the 0. Remember that whenever we talk about something to the 0 is 1, if your instructor is careful, they're going to say a non-zero number raised to the 0 is 1. If it's 0 to the 0, that's actually indeterminate. Same for 1 to the infinity, infinity minus infinity, infinity to the 0. In each of these cases, there's, and I've talked about this in class maybe, but there's a push and a pull going on. So take the infinity minus infinity example. So you've got one expression that's increasing without bound minus another expression that's increasing without bound. So that in itself won't allow us to determine the limit, because suppose that the expression in front is increasing much more quickly than the expression in the back here. The minus infinity part is increasing more slowly, let's say. Well, then the difference between those quantities may be approaching infinity. If they're increasing at about the same rate, then the difference between those expressions may be approaching 0. Or if this guy's increasing faster, then maybe it's approaching negative infinity. But so there's a push and a pull going on, and you have to see how that balances out. Same idea with 0 times infinity. So keep in mind, with 0 times infinity, we're not actually multiplying by 0. You're taking some expression that's approaching 0, so it's very close to 0, times something that's very large. And so again, there's that push and the pull. You're taking something very small times something very large, so it's a matter of which part of that expression is going to win out and determine the overall limit. Or maybe they balance each other out. Maybe not, though. Same thing with 1 to the infinity. Keep in mind, this is not 1 times 1 times 1 times 1 infinitely many times. This is something close to 1. So the base is approaching 1. Numerator is increasing, the exponent is increasing without bound. But so if you expand this, it's not a matter of 1 times 1 times 1 times 1. It's a matter of maybe 3/4 times 4/5 times 5/6, something like that. So that's where you get into a gray area. Okay, so enough introduction. Let's get into some specific examples. So this first limit, I guess it may help if I show you what the graph of cotangent of x looks like. If you've forgotten, you could always type it into Desmos if you want. But it's got vertical asymptotes at 0. It's got another one at pi. And it's a decreasing function. So the graph looks like this, as opposed to, roughly like that, as opposed to the tangent graph as an increasing function. So as x approaches 0 from the right, the value of cotangent of x approaches infinity. So this piece here is approaching infinity times this piece here is approaching 0. So we've got the 0 times infinity situation. And I'm going to save this example for later. So I'm going to box number 2 out here. Okay, so 0 times infinity, that's indeterminate. And we can apply L'Hopital's rule when it's written in this form. So keep in mind, L'Hopital's rule is applicable when you have infinity over infinity or 0 over 0. We'd like to see it in one of those two forms. So the key thing here is it's a ratio. It's not a product. We want a ratio, one thing over something else. So we could use the fact that cotangent is the reciprocal of tangent. So this is equal to 1 over tangent. And so now we can write that as a ratio. So this is the limit as x approaches 0 from the right of x cubed over tangent x. And now if you check the form of that limit, tangent of 0 is 0. So now this has the form 0 over 0. Which means, now we can apply L'Hopital's rule. So this is equal to the limit as x approaches 0 through positives of derivative of the top over derivative of the bottom. And if you don't have the derivative of tangent x memorized yet, and you had 2 weeks off, maybe you just forgot, but remember that very quickly. That's important. That's something that you definitely want to have, top of mind. Okay, so now if you substitute 0, 3 times 0 up top, so the numerator is approaching 0. Secant of 0 is 1, because it's the reciprocal of cosine, and cosine of 0 is 1, so reciprocal of 1 is 1. And so 0 over 1, that's not indeterminate, that's just 0. So the limit, in this case, 0 times infinity is 0, but that's definitely not true every time that's your form. Okay, so we have an answer for that one. Let's look at this limit of x to the x, where x is approaching 0. So this limit for number 2 has the form 0 to the 0. Is that on? Yeah. Okay. Oops. My pen. Okay. No, black. Okay. So 0 to the 0. Indeterminate and not a form where we can use L'Hopital's rule. We'd really like to see it as a ratio. We want to write it in the form 0 over 0 or infinity over infinity. That's with any of these indeterminate forms, think of it like we're headed towards L'Hopital's rule. That's where we'd like to get. But it's an exponential expression, so that's nowhere near a ratio unless we get logarithms involved to get rid of the exponential expression. The inverse operation would be to use a logarithm. Okay, but if I'm going to get logarithms involved, that means I'm going to be changing that function. So what we should do is set a little placeholder. I like to use capital L as a stand-in for the actual limit that we want to solve for. Okay, so we're setting down a landmark, planting a flag at the limit that we actually want to find. Now we can take natural log of both sides. Because natural log is continuous over the set of all positive values of x, I can move the natural log inside of the limit here. For a continuous function, you are allowed to do that. So I can do this. Move the natural log inside the limit. And the advantage of that is now I can take advantage of those properties of logarithms. Let me switch colors here. So that the exponent can come down in front of the log. That's one of your properties, your 3 basic properties of logarithms. So that means that this is equal to the limit as x approaches 0 through positive numbers of x times natural log of x. Which if you check the form now, this is 0 times natural log of 0. Actually, let's look at that. I'm going to get the board all cluttered again. But y equals natural log of x, I graphed it in a previous video, looks like that. As you approach 0 from the right, as x approaches 0 from the right, the value of natural log of x approaches negative infinity. So now this limit right here has the form, well, x is approaching 0, ln of x is approaching negative infinity. So this is another indeterminate form. What we want is to see it written as a ratio. So what if I take this x now and I'm going to move it downstairs to the denominator? So this is equal to the limit as x approaches 0 of ln of x over, instead of putting x over 1 in front here, I'm going to put 1 over x on the bottom. And now we've got it written as a ratio. Natural log of 0, when you approach 0 from the right, again, that's approaching negative infinity, based on my graph I've drawn up there. 1 over 0, so when you have non-zero number of 0, remember that's when it's approaching positive or negative infinity, where if we're approaching 0 through positives, then this denominator is approaching positive infinity. And so now this is a form where we can use L'Hopital's rule. So finally, let me see if I can tilt this screen down and get my plastic bag out of the way. Okay. Finally, now we can use L'Hopital's rule. So this is equal to the limit as x approaches 0 of derivative of the top is 1 over x. Derivative of the bottom So this 1 over x could be written as x to the negative 1. So the derivative of that is negative x to the negative 2. Let's see. Okay, we can do this. Clean this up. So this is equal to the limit as x approaches 0 of, let's see, so x to the negative 2, I'm going to move this upstairs and make the exponent positive. So this is x to the positive 2 on top over x. And I don't want to forget that negative, so there's this negative in front. Okay, but so now I can cancel common factor of x on the top and bottom. And so this is just the limit as x approaches 0 of just x, which is 0. Almost done. That's equal to natural log of L. So natural log of L is equal to 0. If the natural log of our limit is equal to 0, then the actual limit L is equal to, if we do inverse operation, that would be e to the 0, which is 1. Final answer in this case is 1.